So hi guys. So in this discussion, I'll be doing some problems related to this topic, double integrals in polar coordinates. So I assume that you have watched the corresponding lecture video, and I will no longer discuss how things were derived. But to start off, I just want to give you these conversion formulas that we will need. So in here, we have from uh, polar to Cartesian. So we are given the Cartesian, um, we are given the Cartesian form or the polar form, and then we will convert them to Cartesian via the following. We have x equals r cosine theta and y equals r sine theta. Now, if we are given the Cartesian form and we want to convert them to polar, we recall this. R squared equals x squared plus y squared, and tangent theta is equal to y over x. And from here, we can convert double integrals that are in rectangular form to a double integral in polar coordinates. So we will use the following conversion. So if we are in rectangular form, double integral over the domain R of f of x, y, dA, this will be equal to the double integral over the domain R of f of r cosine theta, comma r sine theta, r dr d theta. So again, x equals r cosine theta. So you see here the x, this is your r cosine theta. Y equals r sine theta. So this is your y and this is your r sine theta. Now, the dA, it converts to r dr d theta. Sometimes we write r d theta dr, whichever is more convenient. So this dA here, it can be dx dy or dy dx. Okay, so either way, you will be able to convert it into r dr d theta following the conversion formulas that we have up here. Okay, now the crucial part is the conversion of this region in rectangular form to the region in polar form. Okay, so it is possible that in here, this R here, okay, may be converted. So maybe this R is, say, you have your R equals R1 until R equals R2. And then here theta equals um, theta equals theta 1, theta equals theta 2. And of course, if it is written this way, the inner part here, this is your theta. So this should be written as r d theta dr. And if you interchange the two guys, so if you put the theta in the one in terms of theta on this side, then it will be r dr d theta. So you have to make sure the the arrangement of these guys here corresponds properly to the r dr d theta or r d theta dr. So this is the first case. The other case, for the conversion of the region R into polar form, it is possible that you will have the inner integral will be functions. For example, this could be r equals f sub 1 of theta until r equals f sub 2 of theta, and then here you will have theta 1 until theta 2. And of course, if it is written this way, you evaluate first in terms of r before evaluating in terms of theta. And of course, if you have the other case where your theta is a function of r, and then your R are fixed constants, R equals R1 until R equals R2, then you will have to write the dA or this guy here to be R d theta dr. Okay? So, like I said, the crucial part is the conversion of the rectangular form of the domain to the polar form of the domain. Okay? So, let's work let's do some of the problems that I have prepared here. Let's get this first. So we want to evaluate this integral here using the polar coordinates. So, the standard technique is to identify the domain. If you can draw the domain, which is usually the case for our course, then that will be helpful. So for instance, in here, you have the inner integral is from x until square root of 1 minus x squared. So it's from y equals x until y equals square root of 1 minus x squared. So this guy here, this is just the line, the line y equals x, while this guy here gives you part of a unit circle of radius 1. Okay? So if we try to draw those figures or those functions, you will have, say, you have this, and then you will have the line here, y equals x, and then we will have, say, this is your 1, this is 1 here, and then we will have here part of the semicircle. Okay, so it says y equals x until y equals square root of 1 minus x squared. So y equals x is this guy here. So your y runs from y equals x until y equals x squared. Y equals square root of 1 minus x squared. Okay? So it will be from this point going to this point. Take note, y equals. So the value of y changes. So this will be this part here. These are the y's here. So from this point until this point. Okay? And then you have x equals 0 until x equals 1 over 1 over square root of 2. So x equals 0 until x equals 1 over square root of 2. So we know that this part here, this is your x equals 1 over square root of 2. So it will run now from this point. The value of x will be from this point to this point. But since your y is from this line towards this line here, then your region will be this part here. Okay? So we now have that. Take note. We now convert this region here into polar form. So y equals x. So y equals x. This means r sine theta equals r cosine theta. So if we calculate this, this will become tangent theta equals 1, or that your theta equals 45 degrees, which is pi over 4. Correct? Then, for the other guy, you have your y equals square root of 1 minus x squared. Like I said, this is just the unit circle. So this is just your r equals 1. Okay? But now, the angle, we consider now the region here. The angle will be from pi over 4 until pi over 2. Correct? From pi over 4 until pi over 2. So take note, this is your pi over 4 here. And of course, this guy here is your pi over 2. So we now have, so I'll just write this as capital I equals, we want the integral now. So theta will run from pi over 4 until pi over 2. And of course, your r will be from r equals 0 until r equals 1. Correct? From this point here until that point here. So in here, this will be r equals 0 until r equals 1. And now we put the integrand. So y, that's your r sine theta. And of course, this guy here, x squared plus y squared, that's equal to r squared. And then dy dx, this converts to r dr d theta, r dr d theta. So take note, dr d theta, because in here we have here in terms of r, the outermost is in terms of theta. So anyway, let's solve this. We simplify first the integrand. So integral from pi over 4 to pi over 2, integral from 0 to 1, and we have r to the 4 sine theta dr d theta. So in here, we will have, we integrate in terms of r, integral from pi over 2 to pi over 4, r to the 5 over 5, evaluated 0 to 1, and then sine theta d theta. So this is just 1 over 5 for this guy. And then integral of sine theta, that's negative cosine theta. Then we evaluate this from pi over 4 until pi over 2. And of course, cosine pi over 2, that's equal to 0. So 0 minus cosine of pi over 4, that's square root of 2 over 2. So therefore, this is equal to square root of 2 over 10. So this is the integral given by this expression here. Okay? For our next problem, so this is, again, we evaluate this integral over using polar coordinates. So let us look at the region. So in here, for this part here, we will have x equals square root of 4 minus y squared until x equals y. So again, this guy here, this is just your line. We have converted that already. That's tangent theta equals 1, or theta equals 45 degrees, or pi over 4. For this guy here, take note that this is just a circle of radius 2. So for this guy here, this is r equals 2. So again, for this guy here, this is theta equals pi over 4. Now we have for the outer integral here, we have y equals square root of 2 until y equals 2. So let's see. Sketch. We have the line y equals x or x equals y. And then we have the circle. So this is a 1, this is 2, this is 1, this is 2. So we have this, pardon the scaling, but pretend that this is your circle. Right? Pretend that this is your circle. So anyway, this is the circle r equals 2. This is the line theta equals pi over 4. And then our x or our y, it will be, wait, let's start with x. So it says x equals the circle going to the line. Circle going to the line. So this is the circle. Let's see. This is part of the circle. And then we want to go to the line y equals x. And then, okay, so before we proceed to that, let's check the values of y. Y equals square root of 2 until y equals 2. So this is y equals square root of 2 at this point. Okay, this is your x part, this is your y part. So it will be from, say, this point until 2. This is your 2. So your y runs from square root of 2 until y equals 2. So y runs from square root of 2 until r equals 2. Now, your x runs from the circle to the line. So the region that makes sense is the following. So this is your y equals 2. The region that makes sense is this part here. Correct? So from your circle going to the line. And your y is from square root of 2, which is at this point, until the value of 2 here, until that point. So this is horizontal. Right? All right. So if that is the case, we now have identified the region. So what is this part here? So in polar coordinates, take note that y equals 2. Y equals 2. This is your y equals 2. But what does this mean? Y equals 2. Oops. Y equals 2. This means r sine theta, this is equal to 2. Then we can convert this as r equals 2 over sine theta. Correct? That is your y equals 2. And then, of course, this point here, y equals square root of 2. So this guy here, so r sine theta equals square root of 2, or your r is equal to square root of 2 over sine theta. And of course, your theta still runs from um, let us see, from pi over 4 until pi over 2. So because this part here going to that part. Right? Now, take note that this guy here, we will not need it. We will not need it. Why? Because anyway, if you look at the region, let's say this guy here, this is your R value. So the starting point will be this until this line here. If your R value is on this, you will have this point until that line there. Or here, you will have this point until that point here. Correct? So these are the R values. So if we convert this to polar, what we will have is your R equals 2 going to R equals 2 over sine theta. Theta is equal to pi over 4 until theta equals pi over 2. So again, if we label this as I, this means that I equals the integral from pi over 4 until pi over 2, integral from R equals 2 until R equals, let me write this as 2 cosecant theta. And then what is x squared? What is x squared? X squared, that becomes what? R squared cosine squared theta r dr d theta. And then we evaluate integral from pi over 4 until pi over 2, integral from 2 until 2 cosecant theta. This is r cubed cosine squared theta dr d theta. So here we have the integral from pi over 4 until pi over 2 of r to the 4 over 2. And then here we evaluate from 2 until 2 cosecant theta. We have your cosine squared theta d theta. So we will have here 1/2 times integral from pi over 4 until pi over 2. And then we will have here, so 2 to the 4. 2 to the 4, that's 16. 16 cosecant to the 4 theta over, no, that's not, wait, why is that over 2? This is over 4. This is over 4. This is also over 4. So I have taken over 4 out. So in here, and then minus 2 to the 4 minus 16. And then we have your cosine squared theta d theta. Okay. So if we continue, we will have, let's continue it on the next page. we will have here, there's a 1 over 4. There's an integral from pi over 4 until pi over 2. And then we have 16. Let me convert the cosecant here. The cosecant here in terms of sign. So that becomes 16 cosine squared theta over sine squared theta. And then minus 16 cosecant squared theta. Minus 16, not cosecant, cosine squared theta. And then you have your d theta. We can bring out 16. So we'll just have 4 integral from pi over 4 until pi over 2. Cosecant squared theta over cosecant to the 4, pardon me, cosecant to the 4 theta, that's equal to cotangent squared theta, cotangent squared theta, cosecant squared theta. So do not be intimidated by this guy here. If you look at this, this is easily integrable. Simple U substitution. Whereas for this cosine squared theta, we write that as 1 plus cosine 2 theta divided by 2. And then d theta. Right? So now, if we let u equals cotangent theta, du will be negative cosecant squared theta d theta. So if we integrate cosecant to the cosecant squared theta, yeah, cotangent squared theta d theta. This is just integral of u squared with a negative outside du. So this is just negative u cubed over 3 plus c. Okay? And then we bring back cotangent theta. So for this guy here, we will have 4 times negative cotangent cube theta over 3, evaluated from pi over 4 until pi over 2. And then minus for this integral here, this is easily integrable. We'll just have 1/2 theta, and then integral of cosine, that's sine. So we will have here 1/4 sine of 2 theta over 2. And then again, everything is evaluated from pi over 4 to pi over 2. So I'll just move this guy here on the outermost here, while for this guys here, just move it to the left. So now, at pi over 2 cotangent cube theta, or cotangent cube pi over 2, that's equal to 0. Right? That's equal to 0. So we will have here 4. So at pi over 2, we have 0 minus 1/2 of pi over 2, that's pi over 4. And then sine of 2 theta, and theta equals pi over 2, that's equal to 0 again. So 0 minus quantity at pi over 4 cotangent pi over 4, that's equal to 1. So we will have minus 1/3. And then minus minus pi over 8. and then minus at pi over 4 sine 2 theta, that becomes sine pi over 2. So that's just 1, so minus 1/2. So if we simplify this guy here, negative pi over 4, negative pi over 8, but there's a minus here. So you will have negative pi over 8. And then here we have 1/3, 1/2. So that becomes what? 5 over 6. So plus 5 over 6. Or this is just what? Pi over 2 plus 10 over 3. So this will be the answer for this problem. Okay. Now let us consider our next problem. So we want to evaluate this sum of double integrals using polar coordinates. Now, for this type of problem, of course, you immediately see that there are two double integrals here. So what you can do is to find a way to combine these two double integrals into a single double integral, if possible. Okay. Otherwise, what you can do is to, well, find the double integral here, and then find the double integral here, and then add them together. Okay. So, first, we will try to combine them into a single double integral if we can do that. But in order to do that, you need to observe some things. For instance, you look at the integrands. The integrand here and the integrand here. Take note that they're the same. So it is possible, to combine them into a single double integral. Okay? But now, although they have the same integrands, look at the order of integration. First one here, it's dy dx. The other one here, it's dx dy. So you cannot just combine them. So what we can do is to have them or make them the same order of integration or the same, variable of integrations. Okay. Next thing to do is to, well, try to get the domain of integration. So maybe if we try to sketch the domain of integration, we can see if they actually combine into a single region, okay? Or maybe they overlap, or maybe they are separated, okay? So anyway, let's do that. Let's check first this guy here. Okay, let's check this guy here. So we have your y equals square root of 1 minus x squared for this lower limit of integration. So this one here is a circle of radius 1, only part of the circle. In fact, this is a quarter circle of radius 1. And then for the other guy here, you have y equals square root of 4 minus x squared. This is again a quarter circle of radius 2. So if we try to sketch them into a single, on one Cartesian plane, you will have for the first one, say this is of radius 1 and then 2, 1 and 2. So this is the first one. And then this is the second one, right? So this guy here, it's for this, while this guy here, it's for this. Okay? So it says that your y moves from this part going to that part. Okay? Your y moves from this part going to that part. Y moves from this part going to that part. And notice your x moves from 0 to 1. So indeed, we have this part of the region. Okay? This part of the domain. Okay? That is from 0 to 1, x from 0 to x equals, sorry, your from x equals 0 to x equals 1, and from the circle of radius 1 to the circle of radius 2. So this part here. Okay? Now, for the second one, we have here dx dy. So your x is from 1 until your x is to the circle of radius 2. Right? So for the second one, we have here x equals 1, and then x equals square root of 4 minus x squared. Right? This is your x equals 1. Okay? And your x is equal to 4 minus x squared. It's this part here. Correct? Okay? And then your y runs from 0 to square root of 3. 0 to square root of 3. Y equals square root of 3. If you check this part here, okay, y equals square root of 3. We have, so you got square root of 3 equals square root of 4 minus x squared, or we have your 3 equals 4 minus x squared, or you will have your x squared equals 1. So your x is equal to plus or minus 1. But anyway, your x is equal to 1. So indeed, this value here, is your square root of 3. So it's from 0 to square root of 3, and your x is from 1 to 4 square root to square root of 4 minus x squared, which means that this region here, okay, this region here is actually this part. And as you can see, if you combine the two domains, this part here and this part here, it's actually this region in between these quarter circles. So it will be easier to combine these two double integrals. Correct? And now the region will be what? If you are going to use this region and convert it into polar integrals, your r will be running from 1. Let me write it here. Your r will be from 1 to r equals 2. And then for the theta, it will be from theta equals 0 until theta equals pi over 2. Correct? So theta equals 0 to theta equals pi over 2, which means I'll label this as capital I. Your I now becomes integral from 0 to pi over 2, integral from 1 up to 2 of, we have the integrand x, that's r cosine theta, and then r squared, x squared plus y squared, that's r squared. And then we have dx dy or dy dx, that's r dr d theta, r dr d theta. And this one is really easy. You will just have integral from 0 to pi over 2 integral from 1 up to 2. Take note that this will cancel this guy and this guy. So we just have cosine theta dr d theta, or this is just what? 2 minus 1 integral from 0 to pi over 2 of 2 minus 1. That's the integral from 1 up to 2 dr. And then we have your cosine theta d theta, but this is just sine theta evaluated from 0 to pi over 2, and this is just equal to 1. So this is the value of this integral here. Okay? Now for our last problem. Using polar coordinates, evaluate this double integral here, okay, where R is the region in the first quadrant bounded by y equals 0, y equals square root of 3x, x squared plus y squared equals 4, and x squared plus y squared equals 16. So, for this one, let's check first the regions or the region. So we have y equals 0, so it's this guy here. Y equals square root of 3 minus x. So if x is equal to 1, y is equal to square root of 3. So maybe it's this point. We have this line. And then x squared plus y squared equals 4. So that's circle of radius 2. So 1, 2, 1, 2. So maybe it's this guy here. Not accurate, pardon me, but that's the idea there. And then for the last guy here, this is a circle of radius 4. So 2, 3, 4. 3, 4. So maybe this is 4. If we extend this line here, anyway, and then 3, 4. So maybe we will get this circle here. Okay. Of course, you can extend this to whole circle. This one here also is to the whole circle. But since we are only interested in the first quadrant, then let's just look at the first quadrant. Now, the region is bounded by these 4 equations. So y equals 0 is this x-axis here. This is y equals square root of 3x. And you have these 2 circles. So the region that we are looking, that we require is this guy here. Okay. And now, this guy, we can do this in polar coordinates. What is this one in polar coordinates? So we have what? Tangent theta equals y over x, but y is square root of 3x over x. So this is square root of 3. So this means that theta is equal to pi over 3. Yeah, pi over 3. Sine pi over 3, that's square root of 3 over 2, and then cosine of pi over 3, that's 1. So tangent is square root of 3. And of course, this y equals 0, this is just theta equals 0. And then your circle here, this is r equals 2. And then this guy here, it's r equals 4, which means that this guy double integral of 6 over 2 plus x squared plus y squared dA, we can convert this into the double integral from 0 to pi over 3, integral from 0 to pi over 3, integral from 2 to 4 of 6 over 2 plus r squared, and then r dr d theta. And now this is just simple substitution. Anyway, this guy here does not have, well, this part here does not have any theta. So if we integrate via theta, we just have to subtract this guy here. So we will have what? Pi over 3 minus 0. So that's pi over 3. And with respect to r, we can just have what? U substitution. So if u equals 2 plus r squared, du equals 2r dr. So this guy here becomes integral of 3 over u du. Okay? And if we continue from here, we will have pi over 3 ln absolute value of u. But u is 2 plus r squared, so let's replace that. Pi over, you see, you will have here over 3 and then 3 here. So we'll just have pi. Then ln absolute value of 2 plus r squared. And now we evaluate this from 2 to 4. 2 to 4, so we will have pi times. At 4, we will have 16 plus 2. That's 18. So ln of 18 minus at 2, we have 2 plus 4. That's 16. So ln, sorry, that's 6. ln of 6. And you can simplify this. This is just pi ln of 18 over 6. Or this is just pi of ln of 3. So this is the value of our integral. Okay. So that's the last problem for this set. Thank you for watching. I hope you've learned something or you were able to practice this topic. Bye-bye.